fiber channel storage. So today, the most efficient, the most well-performed SAN would probably be a fiber channel SAN. Now, as I've been telling you before, iSCSI is catching up, but today, if you were to ask me what kind of SAN I would recommend for an enterprise deployment of 100 terabytes or plus, I would definitely recommend a fiber channel SAN. Now, by definition, fiber channel storage architectures provide block-level transfer of storage using SCSI communication over a high-speed fiber network. This is, in essence, the definition of fiber channel SAN storage. Now, as you may know, ESX 3.5 supports a wide variety of vendors for fiber channel storage, among which obviously EMC, IBM, HP, Fujitsu, Hitachi, and many more. And again, we strongly recommend that you consult with the fiber channel SAN compatibility guide on the VMware website for more information before you deploy any of this stuff. Next, let's take a look at the different fiber channel components, what makes up the fiber channel SAN. So let's take a look at the components of a fiber channel SAN. Here you have ESX servers. Each ESX server has one or more HBA cards. An HBA card is a host bus adapter. That's what HBA stands for. You can think of an HBA as a NIC card. The HBA is what connects the ESX server to the fiber channel switch. Now, the second component of a fiber channel SAN is a fiber channel switch, which in essence behaves and acts exactly the same way as an Ethernet switch. Now, a fiber channel switch is also known as the fabric. It is the networking piece of the fiber channel SAN. It is what networks or connects everything together. Now, the third piece is storage processors. Now, storage processors are the front end to the devices, to the physical devices or the LUNs. It is what connects these LUNs or these disk arrays to the HBAs either directly or through a fiber channel switch or through the fabric. So again, the fiber channel switch or the fabric is what connects the HBA to the storage processor, which gives them access to the LUN and to the disk arrays. Now the third or the fourth component here are the LUNs. So what does a LUN stand for? LUN is logical unit numbers, and what it is a representation of the combination of multiple physical storage devices. So you take some of the disk arrays here, or some of the physical disks here, 1, 2, 3 of them, and you make a LUN out of them. You combine the storage of all these three devices, either in a RAID 5, in a RAID 0, in a RAID 1, and you create a LUN. This LUN, in essence, is what becomes the storage, the single storage that is presented to the server as local storage. So you combine 2, 3, or 4 of these disks, you create one LUN, and then you present that LUN to the server as local storage. Now, within the LUN, you can carve up volumes, partitions, etc., whatever you want. And the last component of the SAN are the physical hard disks. This is where it becomes interesting, because in a SAN you can expand the SAN as much as you want. As many trays of hard disks that you can put in the SAN, the bigger the SAN becomes. So the way this works is, you as the SAN administrator, you can take however many disks you want, 1, 2, 3, 10, carve up enough disk space, create a LUN out of this disk space. Now, whenever the HBA or the ESX servers need access to this LUN, they will communicate their request via the fiber channel or the fabric fiber channel switch to the storage processor, and the storage processor in turn will take this request over to the LUN, and in turn over to the disk arrays or the physical disks. Now, in the previous slide we talked a lot about HBAs. Before you buy any HBA hardware for your servers, it's very important to consult with the VMware hardware compatibility guide to make sure that the HBA you're about to purchase is supported within ESX4. Now, traditionally the two most popular types of hardware HBAs have been QLogic and Emulex, but in recent years Brocade and Intel and others have entered the space and are now supported within ESX4. So before you purchase hardware for your ESX host, we strongly recommend that you consult the VMware hardware compatibility guide online. Now, once you're in the VI client, you can click on the configuration tab and then on the storage adapters link, and you're going to be able to identify the different fiber channel HBAs that the ESX host that you're in can see. Now, a little later on, we're going to log into the VI client and we're going to browse through this. But I wanted to mention this here. Now, once you select those HBAs, it's going to also list the different LUNs that this HBA has access to. Again, once we get into the VI client a little later on, I'll show you where this is at and the different LUNs that we have access to. Now in this next slide, it's showing us fiber channel connectivity. Now, fiber channels, or HBAs, the same way as with Ethernet cards today, you can get Ethernet cards that have 4 ports on them, or you can get Ethernet cards that have 1 port on them or dual ports on them. With HBA, you can get also a 1-port HBA, which is, to illustrate the figure that's on the right, you have a host with 2 single-port HBA, which means from the HBA to the actual LUN or the partition that it's targeting, you have one path. If this path fails, you have no secondary path to it. Now on the left, what we have is an HBA with dual port. Now, while with the image that's on the right, you can still provide redundancy, but now you have 2 cards and you're making use of these 2 cards to access the same LUN. So you're taking up technically 2 PCI slots in the host, and you're using them to access the same LUN or the same partition. Whereas on the left, since it's a dual port HBA, you can have redundancy to the same LUN via multiple paths, but you're saving PCI slots and you're also giving access to multiple LUNs at the same time. So whenever possible and whenever cost is not an issue, we strongly recommend you go with dual port HBAs. So moving on here, we're going to talk about zoning. So what is zoning? In very brief, zoning is the grouping of multiple HBAs and then giving these HBAs access to certain LUNs. So you'll take HBAs from ESX A, B, C, and D, you'll group them in a group, and then you'll say, okay, group A has access to the following LUNs. Now obviously it's a little more complicated than this. I'm just trying to make it as simple as possible, and we're going to get into this a little later on. But there's multiple types of zoning. There's soft zoning, there's hard zoning, and there's also something known as LUN masking. And a few slides down we're going to get into this. But again, zoning is performed most of the time at the fiber switch or the fabric level. It can also be performed at the storage processor level, as we're going to see later on. Now to give you an example of how zoning might work, since not a lot of you are going to have the ability to have access to storage, or most of the time in the enterprise the SAN administrators won't even let you near a SAN. But just so you have an idea about how this works. So the same way as, for example, if you're imaging servers and you're trying to pixie boot, a lot of times if you're using software, it's going to detect all the Ethernet cards that it sees. Now with zoning and with SANs, it's kind of the same thing. It's going to detect all of the worldwide names that it can see. Worldwide names pertain to HBAs, as we talked about. So as you can see here on the left, it's discovered some worldwide names. Now the process of zoning is you create a zone and then you add these worldwide names to it, and then you tell this zone which LUNs it has access to. So in the middle, you'll notice that we've included different worldwide names from different hosts in a zone. And then we give this zone access to these LUNs. Now all the way to the right, we've shown you the zones that are existing on the fiber channel fabric. So how are LUNs created, or what are LUNs to start with? A LUN is a logical allocation of storage space carved from a set of underlying physical disks. So what this means in essence is you have 10, 20, 30 independent disks, and what we do is we group them together in a logical manner and present them to a host as single storage. So you might have 10, 20, 30 disks that are each independent of different capacities, and then you group them together, you carve up a LUN of a specific size, and then you present this LUN as local storage to a host. Now you can do RAID 5, you can do RAID 0, you can do RAID 1+0, you can do all types of RAID that are supported on a SAN. So this next slide is actually really cool. Show you how things are done. So as you can see towards the middle here, we have disks. Those are the disks that are available, and you're going to notice that the type or the size of the disks that we have are 4 gig disks. So then immediately under that, you'll notice that we've created LUN 1. Now LUN 1 is RAID 5. So we've added these disks into LUN 1, and then we've striped them as RAID 5, and so on and so forth. Now let's talk a little bit about SAN management. I know a lot of you are looking at these screens, and probably not a lot of you have ever worked on a SAN before, or this might be a little overwhelming. In most cases, in most environments, the SAN is managed by a SAN administrator, by a dedicated SAN administrator, at which point you are not required to manage the SAN. However, why not? If you are given the opportunity to learn a new technology, I strongly recommend that one of the new technologies that you acquire is storage technologies. Everything is moving in the area of storage. Now, while virtualization is awesome, you can quickly see how virtualization and storage go hand in hand. So if you're given the opportunity, if you're not in a large environment where you don't have a SAN administrator that's not going to let you anywhere near the equipment, learn SAN technologies. And if you are in an enterprise environment and you have the opportunity to maybe work alongside the SAN administrator to understand this a little better, it'll help reinforce your knowledge, and it'll only make you know things that you didn't know before, and this in turn translates into making you much more valuable in the outside world, or if you're going job hunting, or if you're trying to get a better job. I definitely recommend you learn SAN technologies and storage if you're given the opportunity. Now let's talk a little bit about access control in a fiber channel SAN. Now every SAN component, such as the HBA or the storage processor, has something called a WWN, or worldwide name. Now a worldwide name, you can think of a worldwide name as a MAC address. The worldwide names are assigned by the SAN manufacturer. Now the worldwide names are useful for SAN administrators in order to identify the equipment for zoning purposes. Now a worldwide name is a 64-bit address. The format is as such. Over here. This is an example of what a worldwide name looks like. Now let's talk a little bit about access control. What if you had a lot of LUNs and you needed a way to prevent certain ESX servers from accessing certain LUNs, or even preventing some ESX servers from viewing or even acknowledging that there is a LUN that's available that they can attach to? How do you control that? What are the methods that are available to you? Now there's a few ways of doing this. There's actually 3 ways of doing this. You can either let the SAN administrators, if it's another group in your organization that handle that, you can let the SAN administrators control access to the LUNs, or you can ask the SAN administrators, hey, give me a chunk of LUNs, let's say 5 or 6 or 10 or 20 LUNs with these sizes, and I will control access and visibility of these LUNs to my ESX servers the way I want. ESX gives you the ability through the ESX software to control access or to control the visibility of SAN LUNs. Alright, so let's examine soft zoning. Soft zoning is the first method of access control or LUN visibility that we're going to talk about. What soft zoning does is the storage processor controls the visibility of LUNs based on worldwide name. So the storage processor here, for example, says that the following worldwide name, which belongs to HBA 1, since we're going to make this 1 and this 0, HBA 1 with worldwide name as follows cannot see LUNs 4 and 5. This is called soft zoning, when the storage processor controls the visibility of LUNs to the HBAs or to the ESX servers. Hard zoning occurs at the fiber switch level or the fabric level and is known as zoning or hard zoning. Hard zoning is the control of the visibility of storage processors based on a per port basis. So a fiber switch here has 1, 2, 3, 4, 20 ports. The fiber channel switch here says, for example, that port 10 cannot see storage processor 0. And in this case, we're going to make this storage processor 0 and this storage processor 1. So port 10 cannot see storage processor 0, and in turn, storage processor 0 is the storage processor that has access to LUNs 1 and 2. So the access control in hard zoning happens at the fiber switch or the fiber channel switch level. Now the third option is LUN masking. LUN masking can happen either at the storage processor level or at the hosts themselves level, which means that it controls the visibility of LUNs based on hosts. So you can configure, for example, ESX01 not to be able to see LUNs 3 and 4. You can control this either from the host itself or at the storage processor level. And that's why I named this host access. But the true name, or the correct name for this, is LUN masking. So you prevent the access or the visibility of certain LUNs based on hosts. Now when addressing fiber channel SAN LUNs, the name formatting is a 4-part name as follows. It starts off with the HBA, the device that's being used. So for example, every HBA device is going to have a number. It's going to be preceded by VMHBA and then the number, whether it's 0, 1, 2, 3, 4, whatever it is. Then the storage processor number is going to follow, so that's the route it's going to take in order to access the LUN or the partition. Next comes the destination LUN number, and after that is followed by the partition number. So in the examples that we have down here, we have VMHBA0 trying to get to LUN 8, partition 1 on LUN 8 actually. So the route that it's going to take is VMHBA0, that's the device number that's given to the VMHBA, to the HBA cart on the ESX host. It's going to go from there to storage processor 0, then it's going to access LUN 8, and from LUN 8 it's going to gain access to the first partition or partition 1. In the second example, we have VMHBA0. Again, we're using the same device on the ESX host. It's going to access, again, storage processor 0. It's going to get to LUN 9 and in turn to partition 1. However, if you look closely to the second set of examples that we have, we're using VMHBA1 via storage processor 1 to get to LUN 8 and in turn to partition 1. And we're doing the same thing for LUN 9 to partition 1. Now this provides some kind of redundancy to access the LUNs and the partitions that are on them via two different storage processors, two different routes, thereby creating what's known as multiple paths to a certain LUN. Now let's go to the whiteboard and take a look at a few more examples of how we can do this. So let's take a closer look at LUN addresses and at partition addresses. So an address is in essence a route. How does V8 or HBA0 get to volume 2, for example, or partition 2, or even LUN 1 or LUN 2 or LUN 3? So here's the format. In the first example, we have HBA0, which here represents VMHBA0, connecting through the fiber switch or the fiber channel switch, the fabric, to storage processor 0, which means VMHBA0, storage processor 0, LUN 1. Very, very simple. No confusion here. So VMHBA0 connects through the fiber channel switch to storage processor 0 and in turn connects to LUN 1. In the second example here, we have HBA1 connecting again through the fabric to storage processor 1 and in turn connecting to LUN 3. So now, if HBA0 wanted to connect to LUN 2, what would be the proper syntax? I'm going to pause the video here, think about it, write it down, and when I start the video again, I'm going to give you the answer. So what we're trying to do in this exercise is we're trying to connect HBA0 through the fabric to storage processor 0 and in turn connecting it to LUN 2. So what would be the proper address? It would be VM HBA 0 connecting through storage processor 0 and then connecting through LUN 2. If that's your answer, you get a cookie. It was correct. Now let's take a look if you wanted to have an address that went one step further to one of these partitions inside the LUN. So let's take a look at the first example here. Here we have VMHBA0 again connecting through storage processor 0, connecting to LUN 1, and in turn connecting to partition 1. The second example connects VMHBA1 through the fabric to storage processor 1 to LUN 3, and in turn connects to the only partition available, which is partition 1. So now, what would the address be if I wanted to connect HBA1 through storage processor 0 connecting to LUN 2 and in turn connecting to partition 2. Again, I'm going to pause the video, go ahead and write it down, and when we get back, we're going to give you the right answer. All right, let's see if our answers match. We're connecting VM HBA1 through storage processor 1, all right, or through storage processor 0. My fault here. Yep, you can laugh at me. It's okay. It's through storage processor 0, through LUN 2, and again through partition 2. So again, if you wrote this down, I was wrong, you were right, and again, you get a second cookie now. So why do you need all this? Why do you need the addressing and the masking and all that stuff? Because later on, when we're trying to configure our LUNs and our storage inside the ESX system, you will need these addresses in order to mask certain partitions or certain LUNs. You're going to need to tell ESX server what to be able to access and what not to be able to access. And the only way to do that is if you know how to get the addressing properly and correctly. Don't tell me this is not fun stuff. This is cool and this is exciting. So let's push forward now. Alright, now so far we've been talking about fiber channel SAN. Now fiber channel SAN implementation in an enterprise can be costly from several angles. First of all, in order to implement a fiber channel SAN, you need to implement a new architecture. You're going to need fiber channel switches, you're going to need HBA cards for your servers, and you're going to need a fiber channel storage devices. So it's expensive because the devices are expensive, the components are expensive. You're going to need to run fiber cables. You're also going to need to learn or acquire new knowledge on how to administer, how to properly configure a fiber channel SAN. All of those can pose challenges in an enterprise. So are there any other solutions other than a fiber channel SAN? Yes, there are. And one of those solutions is iSCSI. iSCSI stands for Internet Small Computer System Interface, is an alternative that's quickly gaining popularity in the enterprise. And for good reason. Number one, it's much cheaper than fiber channel on all levels. Components or non-components, it's cheaper in terms of disk as well. Number two is with iSCSI, you can use or leverage existing network infrastructure. Now because iSCSI goes over standard IP or TCP/IP, you're using existing Ethernet cards, you're using existing Ethernet switches, you're using your infrastructure, your existing network infrastructure to leverage this powerful storage device that you can implement. Routing, authentication, and encryption is also handled by TCP/IP. Education, you don't need to be educated on all these components. You're already familiar with IP routing, authentication, and encryption. So you don't need to introduce something or a new component to your environment. You already know this stuff. You're just reinforcing it and adding another component or another piece to the puzzle here. iSCSI is also internet ready, which means you can connect two geographically separated data centers using iSCSI. You have the capability of connecting a data center that's in Chicago with a data center that's in Las Vegas, for example, leveraging the internet. ESX server allows you to use iSCSI to boot from SAN. This is exactly the same as with the fiber channel. As long as you have an iSCSI hardware initiator or an iSCSI HBA, as we're going to cover in a bit here, you can boot off of a SAN LUN. Now one thing I want to stress here, you can only boot to SAN when using iSCSI if you're using a hardware initiator or a hardware HBA. You cannot boot to SAN if you're using a software initiator. Alright, so let's take a look at some of the iSCSI SAN components. You're going to quickly notice here that there's several similarities between the iSCSI SAN components and the fiber channel SAN components. So let's take a quick or closer look here. Inside of an ESX server, you can have either an iSCSI HBA controller, also known as an iSCSI hardware initiator, or you can have an iSCSI software initiator. Now this is self-explanatory, but I'm going to go into a little bit of details. An iSCSI hardware initiator is similar to an HBA. It's an iSCSI physical device that you install in a server. An iSCSI software initiator is software generated or installed in order to replicate or initiate an HBA or an iSCSI hardware initiator. What's an HBA hardware initiator or an iSCSI hardware initiator? It's a NIC card. Now with software it allows you to use the existing NIC card, but with software you can turn this NIC card on or make it multifunction in order to become an iSCSI initiator. Now second, you have the IP network instead of the fiber channel fabric or the fiber channel switches. Here we're using the IP network, the Ethernet switches that we currently have, the existing infrastructure that acts as the fiber if you compare it to the fiber channel SAN. On the other hand, you still have, or on the other side, you still have the storage processors for the disk arrays. Now again here, I didn't go into much details when we were talking about fiber channel SANs, about storage processors, but you can have those in either active mode or active passive mode, but I'm not going to go into a lot of details about that. You can feel free to research this over the internet and see how you can configure those in numerous ways to either be active or active passive. And again, you have the LUNs and the actual physical disks. Now you're going to notice here that I specified targets. Now with an iSCSI SAN, we call the disk array a target. Now why do we do that? There's a reason for that, and that is because a disk array in the sense of a fiber channel SAN is a grouping of disks that are in disk trays, for example. In the case of an iSCSI, you can turn any storage device that's attached to any server into a LUN or into a usable iSCSI storage device, provided that you have the right software installed. So let's say you have a server here that has local storage, for example, worth 200 gig. If you install the right software on the server, then you can connect it via iSCSI and have other devices use the local storage attached to the server. For this reason, we call the storage targets and not disk arrays, because in many cases they're not disk arrays and they can be local storage or any other kind of storage that is attached to a server. Alright, now let's examine iSCSI addressing a little bit and see how we can compare that to fiber channel addressing. Now with the fiber channel, we had the WWN or the worldwide name, which is similar to the MAC address. With iSCSI, we have the iSCSI node, which is the way to identify the devices, the initiators, whether hardware or software, or the storage processors, or the targets. Again, I say targets here after I said storage processors because a target can be either a storage processor that's connected to physical disk arrays, or it can be any server that has a local attached storage that you wanted to use via iSCSI, provided that this server has specifics or special software to make it usable by iSCSI. Now the way to construct the iSCSI address is the string first is started with an IQN. IQN stands for iSCSI qualified name, which in the example string down here is IQN dot. Then it's followed by the date, and the date consists of the year and month when the organization registered the domain name. In our case, the domain name is eliaskinaser.com. So for example, the year we've registered this domain name is 2006, the month is December or 12. So the string so far consists of IQN.2006-12 dot and then the domain name or the subdomain name in reverse. So in our case, it's .com.eliaskinaser. Then after that, you can follow it with a column and an organization or an enterprise specific and unique name. In my case, or in our case, we selected ESX1. I stress again, this name has to be unique in the organization in order to be able to identify this node. Okay, so you're probably asking me now, how does iSCSI discover LUNs? And that's a good question. iSCSI discovers LUNs or targets in two ways. First, static configuration, whereby you provide the IP address, the TCP port, and the iSCSI target name. All of this would be available information to the initiator, at which point it would know how to connect.
Or the second option, which is known as send targets. In this option, the initiator uses the target's IP address and the TCP port to establish a discovery session. Once the session is established, the initiator then uses the send targets command to find out more information about the iSCSI target's available LUNs or available storage. Now it's very important to note here that hardware initiators will support both these options, whereas software initiators will only support the send targets configuration. Since iSCSI uses TCP/IP to send data or as a way of changing data from one site to another or exchanging the data from one site to another, we have to find a way to encrypt or authenticate or protect this data. So we can use CHAP, which is a protocol. CHAP stands for Challenge Handshake Authentication Protocol. This allows a password to be entered without having the password to be transferred over the network and be compromised at that point. Now, it is also good practice when using iSCSI to isolate it on its own LAN or on its own VLAN, which is in most of the cases a VLAN will be used to isolate the traffic that's being used for iSCSI. Now, we've been talking a lot in this module, so how about we just drop some of this mumbo jumbo. Let's log into our VI client and see how we can set up an iSCSI software initiator. Alright, so we've logged in with the vSphere client. Now the first thing we want to do is we want to make sure that the software iSCSI initiator is enabled. And to do that, we're going to go to the host and clusters, and then we're going to go to the configuration tab, and we're going to click down here on where it says security profile. Now you can check within the security profile to what's running and what's enabled and what's not. And if you don't see the software iSCSI initiator, you can click on properties up here, and we're going to enable it. That allows us access to use it. Now, where would I go to configure the software iSCSI initiator? Would I go to storage or would I go to networking? Now, the obvious choice might seem that, okay, well, I'm trying to work with storage here, so I might have to go to storage. But remember what I told you. iSCSI is based off or leverages existing Ethernet and IP networking. So in this case, we're going to actually go to networking in order to take the first step to configure iSCSI. So the first thing we're going to do when we get to networking is we want to add a port group that allows iSCSI to communicate with target storage. So the way I'm going to do that is I'm going to click on the properties of an existing virtual switch here, and I'm going to click on add. And of these three choices for port groups, which one would you think is the right one? Now obviously some of you are going to say iSCSI obviously because it's written here, so I'm actually going to select the VM kernel port group. We're going to click on next. And then you can give this a name. In my case, I can give it IP storage. I'm going to leave the VLAN blank for now. And we're going to IP it. So I'm going to give it 10.4.14.50. And let's give it a default gateway or a subnet mask as well. We're going to click on next. And finish. Alright, now that we've configured access to target storage, we're going to click on close to get out of here. We've configured a virtual switch, so we've told the iSCSI software initiator how to communicate, how to use virtual networking in order to get to its storage. Now we need to configure targets. Now we need to be able to tell it, well, where do you go to get access to these iSCSI LUNs? So now that we've configured the iSCSI software initiator as a storage adapter, I can click on the storage adapters here. And now I'll be able to configure my software iSCSI to point to targets. Now the way you identify your software iSCSI, aside from it being listed under the iSCSI software adapters here, is you'll notice that VMHBA 33, or sometimes it's 32 depending on the installation of your system. That's how you identify that from Fiber Channel cards, which are going to be identified as such, VMHBA 0, 1, 2, 3, depending on the PCI slot that device takes within the server, it gets identified that way. But software iSCSI initiators are typically VMHBA 32 and above. That's an easy way for you to identify them. Alright, now that we've selected the VMHBA card that is the iSCSI software initiator in our case, what we're going to do is we're going to click on properties down here.
And it brings us to a screen that allows us to configure the different settings for iSCSI. Now the first thing we want to do is obviously we want to enable it, because as you see here it's disabled. So we're going to click on configure, and by enabling it, it allows us to do CHAP authentication and access some of the more advanced features. So we're going to click on enable. Once you enable it, it obviously allows you to change the name if you need to. I'm going to keep it as default for the purposes of this example. I'm going to click on OK. It'll take a second here, and then you'll notice that automatically CHAP and advanced have become available. Now we'll talk about those in a second. Now up here you'll notice that during the presentation we talked about the different types of ways iSCSI can discover LUNs. You can either discover LUNs via dynamic discovery, or you can put a static route and tell it, well, you're going here and you're assigning it a name. So let's go ahead and do a dynamic discovery here, and I'm going to click on add, and we're going to do 10.4.14.55. Now over here it allows you to configure CHAP if you need to as well, but we'll leave CHAP for the next few seconds here. So I'm going to click on OK, and it should list it here in a second. Okay, well there it is. Now we're going to click on close, and you'll notice that it'll automatically prompt you to rescan, because automatically after you add a target you need to rescan your HBA cards, or in this case your iSCSI software initiator, before it can see those LUNs. So I'm going to say yes here, and voila, there is the LUN. Alright, now let's go back into properties here and talk a little bit about CHAP authentication. Now with CHAP authentication you have two methods of doing CHAP. You could either allow the target to authenticate the host, which is the first option that you'll see up here, and with this you have several different options. You can either obviously not use CHAP, which is the default, or you can do not use CHAP unless required by the target, and the third option would be here to use CHAP unless prohibited by target, and use CHAP. So the first two options are kind of self-explanatory. Do not use CHAP unless required by the target. So unless the target requires CHAP authentication, don't use it. So it's kind of optional here. You check with the target. If the target requires CHAP, you authenticate. If the target doesn't require CHAP, you're good. And then the second option, which is highlighted here, which says use CHAP unless prohibited by target, which means you're going to always use CHAP unless the target says I don't want to use CHAP. And then the fourth option here is use CHAP, which means you have no option. It's a dictatorship. You're going to use CHAP. For this option, you have the ability here to set a name and a secret, and that secret would obviously have to be authenticated by the machine that's actually trying to access the target. Now that's one way of doing it. Now the second option here, which is mutual CHAP, which means the host also has to authenticate the target. And down here you don't have a lot of choices. It's either do not use CHAP or use CHAP. It's very simple. And then you have the same thing. You put a name and you give a secret. So for the purposes of this example, we're just going to keep this as defaults, and we're going to leave it the way it is. Focusing our attention now on the Advanced tab. Obviously the Advanced tab allows you to do advanced settings as far as the iSCSI software initiator is concerned. So the two main things I want to focus your attention here on are the header digest and the data digest. And both of those are error correction methods for the iSCSI protocol that allow you to protect the integrity of the header and data of the iSCSI protocol. And they allow you to protect the integrity and do error correction beyond what the traditional IP or TCP networking layers will do. So this is another extra step that allows you to protect the integrity of the header and the data from end to end, and allow you to do error correction. Now obviously by enabling these two features, you're gonna take a performance hit, and that's why the Intel Nehalem processors are strongly recommended, because you're able to offload some of that. Now you can feel free to browse through the rest of the advanced options and tweak them as you need to, but for the most part, if you're using iSCSI, with the exception of enabling or disabling the header and the data digest, for the most part these settings are pretty much static, and you probably won't need to touch them unless you come into a troubleshooting or you're seeing some performance issues where you would have to tweak the iSCSI software initiator or the iSCSI protocol a little bit. So we're going to click on close to exit out of here. So there's one more thing I want to mention here before we move on to NAS and NFS storage. For those of you that are taking the VMware VCP4 exam, you need to know, and we talked a little bit about this during the lecture, You need to make sure you know that if you're trying to boot ESX to SAN, you can only boot ESX to SAN if you're using the hardware iSCSI initiator. You can't boot an ESX host to SAN using the software iSCSI initiator. And the second thing that you need to know is the LUN that's being presented to the ESX host in order to boot ESX to the SAN has to either be LUN 0 or LUN 255. These are the only two LUNs that would allow ESX to boot to SAN. So just keep that in mind if you plan on taking the VCP4 exam. That's almost a guaranteed question, but also keep that in mind if you're trying to configure ESX to boot from SAN. Alright, enough with iSCSI. Now let's focus our attention on NAS and NFS storage.